Hello and welcome to PSIRDEMATICA. In this video, we'll be looking at parallel computing. Now this is the second video of the Introduction to Parallel Computing series. I'm Joseph Sedem, a tutor at PSIRDEMATICA. We are glad you are learning parallel computing with us. Now in this particular video, we would talk about what parallel computing is, and then also discuss the concept of distributed memory, and as well as talk about the concept of shared memory. But before we start, we first have to make some assumptions, right? So first, know that when I mentioned the word CPU, I'm referring to the physical hardware, right, that is inside your system unit or your laptop, the physical hardware. And then when I mention the word processor or core, I refer to the component of the hardware that performs the computation or the processing, right, in your machine or in your system. So, and then we also have to assume that the one core, right, or one CPU in the past only performs a process at a time, right? That's the basic assumption. And then also we also have to talk about the fact that the next process only starts after the previous process has been completed. These assumptions are just made for the purpose of better understanding, so bear with me. Now in the previous video, we made mention, or we laid emphasis on serial computing, and then we spoke about how these hardware manufacturers had to push the limits, right, in order to make serial computing or boost the speed of serial computing. And then we spoke about the virtualization, the vectorization, the multi-threading, hyper-threading, and all those things. But then we realized that still the computational speed, right, or the power needed to process the current data we have was still not enough. So we had to introduce a concept called parallel computing. So what is the parallel computing? What is it? Now parallel computing is a simultaneous execution of the same task, which is split into subtasks on multiple processes in order to obtain results faster, right? So basically what parallel computing is that, assuming you have an app, right, or you have a code which is supposed to return the area of some figures, right? Now in this code or in this app, you need to return the area of a triangle, the area of a square, and probably the area of a trapezium. Okay, and then you need all these things to be executed, and then their answers returned, right? On a serial computer, it means that when running this app on the serial computer, the area of the triangle will be executed, the answer will be printed or shown, then the area of the rectangle or the square will be printed, will be computed, and then the answer will be shown, and then the area of the trapezium would also be computed. But then the problem with this is that, should it take, let's say, a week or a day for the area of the triangle to be processed, it means that we would have to wait for a day to get the answer for area of a triangle, wait for another day, and then another day. So in total, this would take 3 days to process, right? But then the parallel computing is saying that the simultaneous execution, so which is that you execute these tasks, right? You execute these tasks simultaneously, but then we are supposed to split these tasks into subtasks, so subsections, and then these subsections are then processed on multiple processes, which means that yes, we could have this whole program or this whole code, but then this code they would be split into sub tasks, right, where each task would be a separate computation. So this could be the area of the triangle, area of a square or a rectangle, the area of the trapezium. Now these tasks are all included in this, right? But then we are supposed to write a code in such a way that once this task is being run by multiple processors, each processor would be running different computations simultaneously and then return their results once they are ready. So instead of spending 3 days to compute this whole area, we could just spend a day, right, in computing the total area or all the areas together. So basically that's the concept or the idea behind parallel computing. Simultaneous execution. Bear in mind, the same task, you have the same file, the same code is executed, but then this time around it is executed by multiple processors. But then in order to make sure each processor compute the task, you have to first split the major tasks into subtasks or subsections such that each processor can know what to do and perform the computation accordingly. Okay. Now, in order to, how do we then perform the parallel computing? In order to do that, we will need a parallel computer architecture, right? Obviously, we can't just, bear in mind, we need multiple processors. So we can't do this on a uniprocessor or with a single processor. And then we would also need a parallel algorithm or a parallel program, which means that our code would have to be written in a special way that the tasks would be divided into sections, and then let the processors know, or each processor know, which part of the main task is supposed to compute. And as well, in order to get these parallel algorithms, we would have to perform parallel programming, right? So SIRDEMATICA has some series or a set of series on parallel programming with C or in Python, so you can go and then watch that. I'll show the link to the video here in this section. Okay, so now these are the things we need in order to perform parallel computing. So talking about the parallel architecture, right, looking at this image here, this is an image of the Beowulf parallel architecture, where we have the output device, all right, and then some system units combined, right? So from the previous videos, we spoke about having unit processor systems. So assuming this is a system unit that has a CPU with its memory, and then there's another system with a CPU with its memory, and then another processor with a CPU with its memory, right? Now these machines have been connected together, which means that in total, if you have 2, 4, 6, 8, 10, 12, 14, so there are 14 systems combined, and assuming each has a uniprocessor, it means that we will be having 14 processors at our disposal, right? Or 14 CPUs at our disposal. Bear in mind, in this situation, a processor is a CPU since it's just one, it has one core. So it means we have 40 processors at our disposal, right? So this is a basic parallel computing architecture, which is that in order to get a parallel computing architecture back then, you would have to combine multiple computers, right? Since these computers have just one processor in them. Now, the combination of these multiple computers, right, introduce a concept or a notion called the distributed memory. So let's look at that. So assuming this is our head or our master, right, and then this is the machine or the system on which the main area program is written, right, and then we want to divide this main area up into sections where we can let these machines or these other systems run, right? So first, from the previous video, we said that in order to run or execute any task or any process, it first has to be loaded into memory, which means that this whole file or this whole algorithm or program would first have to be loaded into the memory of the head node or the main processor, the one which is supposed to send or ask the other processors to compute, right? But then once the instruction is being sent, bear in mind that it's loaded in the memory of this machine or this system and then being processed by this CPU. Now for this information to be sent, it has to go to this system, right? But then for this system to know that, okay, I'm supposed to calculate for area of a triangle, right? It first has to keep the information that it's supposed to do or the data in its memory. And then for this other one, this would also have to keep, let's say, area of a square, keep its information in its memory, and this as well. Now the concept or the idea behind this, bear in mind that the data or the computation they have to perform are being copied from this memory or transferred from this memory to their corresponding memory for each processor to work on or to process on. So this concept of taking information or data from one memory that is serving as the head or the main memory to their corresponding memories in different machines, right? Different machines. So these are different systems, right, that are connected together, and then each system has its CPU and memory. So the movement of data from this system into this system, right, and then into this system, and then into this system is the notion of the distributed memory. So basically the distributed memory just moves or distributes data or set of instructions from the memory of the main node which into the memory of the server nodes, right, or the compute nodes, and then their processors also execute the tasks. So basically that's the notion of distributed memory. But then looking at this, combining multiple PCs or multiple systems, right, is quite expensive, which means that a layman or a normal regular person would find it difficult in doing it, even getting the machine and all those things alone in combining or creating our own high performance power computer architecture is expensive, right? So the hardware manufacturers thought it wise to introduce the multi-core processors, right, which means that this time around, instead of combining 4 machines or 4 systems together, we can have a system that has 4 processors combined. So the around 2005 we had the dual cores, the quad cores, the octa cores, the coming in. So now you can hear of a machine with dual core, octa core, hexa core, and all those things, which means that what now these machines have one CPU. Bear in mind I said the CPU is the hardware, and then the computational cores could vary depending on your system and the manufacturer. So basically now we could have one machine or one system with what different types of cores, which would now behave as though you have 4 systems combined or 4 machines combined. Now the introduction of multi-core machines, right, or multi-core processors into machines also brings about the idea of the shared memory system or the tightly coupled systems, right? So in this situation, we could see that we have a system, right? This is a system, and then this system has 4 cores. So starting from core 0, core 1, core 2, and then core 3. Now we said that each core has its cache where it stores the data that it uses frequently, and then the whole CPU or the processor needs a memory in order to function properly or process any data for us. Now here lies the case, there are 4 cores on one CPU, Bear in mind, we said CPU refers to the hardware, so there are 4 compute cores on it. And then these cores are supposed to perform tasks independently before combining their final answers. So we have our area up here, and then area of a triangle, area of a square, and then area of a trapezium here. Now, should this task, right, this, let's say processor 0 or core 0, be the one serving the others or telling the others which parts of the instructions to run, it means that the information or the data that the processor 0 will be working on would have to be transferred, right, to the other processors. But here is the case, all these processors or all these cores are in one CPU, and if these cores are found in one CPU or on one CPU, it means that they all have a common memory, right? So in this situation, the sharing of information will still be within one system or one system unit, but then transferred, right? So it's now going to be shared between or amongst the cores that are available or the cores that are supposed to engage in the computation, right? So this idea or this concept is the concept of the shared memory. So the information is here, right? So these cores are supposed to compute their independent areas. So let's say the area of a triangle, area of a square, and then area of a trapezium, right? But then the data they need to perform these computations vary. So they all come to this side of the memory, take the information, the data they need, and then use it to compute. So this guy will come for the data it needs for area of a triangle, this guy counts for the data it needs for area of a square, and this guy counts for the data it needs for what? Area of the trapezium, and then keeps them at a portion. Bear in mind, this is being run as processes. So since they are being run as processes on each core, they all need an address or a specific place in memory. So the core 1's address in memory or a specific place in memory will vary for the core 2's address, and it will vary for core 3 address. Bear in mind that all this is happening in one system. So the idea of them all going to the address of core 0 to take the data or the instruction they need to compute independently is the shared memory, right? So the shared memory concept, basically that's that. Okay, but then we realize that the combination of multiple uniprocessor machines, right, in order to get this parallel architecture or getting one system with multiple core architecture, would it be enough? Because we will still need because the data that is being generated is high, and then we need to save time in the computation, right? So it means that we need faster computational power and then powerful processing speeds or processing capabilities. In order to do that, we would have to look for a way to combine these multiple processes, right, to work together, right? So in the next video, we would look at parallel computing with multiprocessors, where we see how multiple processes are combined together to perform parallel computing tasks, right, to compute in parallel that communicate with each other. That will be all for this video. If you really enjoyed this video, please don't forget to like and subscribe and share with your friends, and I'll see you in the next video. Thank you.